Good morning, dear students.
Good morning, sir.
Yes.
Morning, sir.
Okay.
Good morning, sir.
Thank you. Good morning. So, we'll proceed with thermodynamics. In the last, I think, two classes, one class, we have covered some of the concepts in thermodynamics. Just surf through all the concepts that we have covered in previous class. Okay. Uh, First, we started with the definition what is in thermodynamics. Then, different types of system open. Okay. This one. You have been signed out. So system surrounding boundary and types of system open, closed, isolated conditions. If both matter and energy is exchanged, open, neither matter nor energy isolated, only energy it is closed. Okay. So process, different types of processes, isothermal, adiabatic, isochoric, isobaric, reversible, irreversible, cyclic, right? What is state of a system? It is the condition expressed uh, by giving definite values for certain variables like temperature, pressure, volume. It may be solid, liquid, gaseous state of a system, right? State variables, so state functions, extensive and intensive properties, internal energy concept, and then first law of thermodynamics, mathematical form, delta is equal to Q plus W or W plus Q. No problem. So sign conventions, any loss is negative, any gain is positive. And for first law, when we apply it for isothermal process, delta U becomes minus Q. For adiabatic process, delta U becomes W because Q is equal to 0 there. Expressions for work done in reversible isothermal processes minus 2.303 nRT log V2 by V1. Result is P1 by P2. Or in terms of adiabatic process, work done is equal to W is equal to NCV dt. So, it is for compression T2 minus T1, for expansion T1 minus T2, because higher minus lower, higher temperature minus lower temperature, and CV molar heat capacity. And if a gas is being expanded or contracted against a constant pressure and at a constant temperature, then W is equal to minus P external into delta V also can be used to calculate work done. Then we had this, one second. You don't know. It is sometimes it becomes suddenly irresponsive, non-responsive. Oh, one second. Oh. Then we had thermochemistry. Thermochemistry, particularly a branch of thermodynamics, which deals with heat predictions and heat changes during a process. Enthalpy is the heat content, which is equal to U plus PV. Okay. So enthalpy change can be calculated as H2 minus H1 or HP minus HR. Correct. Then we had this thermochemical equation, a balanced chemical equation in which physical states of reactants and products are indicated along with heat change. That is what is thermochemical equation. Based on whether heat is liberated or absorbed, there are two types of reactions, exothermic and endothermic. Delta H negative exo, positive endo. Then enthalpy of reaction definition. Write a balanced equation. If reaction takes place completely as per the balanced equation, whatever the enthalpy change is there, it's called the enthalpy of reaction. At 1 bar pressure under given temperature, then enthalpy of reaction delta RH is same called as standard enthalpy of reaction delta RH, not like. So factors influencing enthalpy of reaction like nature of reactants, physical states of reactants, also products, allotropic forms. Different allotropic forms will have different enthalpy change. Temperature of the reaction. Then you should know heat change at constant volume and constant pressure are considered as volume is delta U, heat change at constant pressure is delta H. So then comes relation between delta H and delta U. From H is equal to U plus PV, you can derive delta H is equal to delta U plus P delta V or plus RT delta N. What is delta N? It is number of moles of gaseous products minus number of moles of gaseous reactants. So how to find delta H and delta U relation? And for a given reaction, if NP, number of moles of gaseous products, is less than reactants, then there will be always delta H less than delta U. If NP is equal to NR, delta H is delta U equal to delta U. And if number of moles of gaseous products are greater, then delta H is greater than delta. Now there are different definitions we need to take up, different types of definitions. In a particular reaction, it is balanced, reaction is taking place according to balanced equation, then whatever the enthalpy change is there, that is called enthalpy of reaction. It is a general terminology. But in that reaction, there may be certain amount of compound being formed. There may be certain amount of compound being burnt, combusted. There may be certain amount of solute being dissolved. During that process, anything can happen, right? So a reaction may indicate any process. Depending on what is exactly happening during the reaction, different definitions are there, like enthalpy of formation, enthalpy of combustion, enthalpy of transition, solution, bond enthalpy, neutralization. So during each particular type of reaction, there is a particular enthalpy change which is going to be defined now. You need to remember under each definition, how do we exactly write a reaction for that? Okay, let us see what you mean by that. Okay. First one, different heats of reaction or enthalpies of reaction. First one, enthalpy of formation. Enthalpy of formation, delta FH. Standard enthalpy of formation, delta FH naught. That's all. Now, as per the definition, what is enthalpy of formation? It is a change in enthalpy when 1 mole of a compound is formed of that substance. Is formed, 1 mole should be formed, but condition is from formed from its elements. From its elements only. Then only that reaction can be called as enthalpy of formation. Enthalpy change can be called as enthalpy of formation. For example, if you want to write a reaction representing enthalpy of formation of water, you need to write formation of 1 mole of water. Right on the product side, 1 mole of water. This water must have been formed from H plus and OH minus ion combination, or H2 plus O2 combination, which would be correct. Because when H plus combines with OH minus, water is formed. When H2 combines with O2, then also water is formed. Which should I take as reactants? H plus OH minus or H2 plus O2?
H2 plus O2.
Because
2 plus O2.
from its elements, not from ions. So that is the condition. So you should write reactants H2 plus half O2. Okay, let's write physical state, thermochemical equation we have to write. This is liquid. And whatever the enthalpy change is there, that is generally called enthalpy of reaction. Since this reaction satisfies the condition of definition of enthalpy of formation, this enthalpy of reaction is nothing but the enthalpy of formation, and it is equal to minus 286. Enthalpy of reaction. Fine. So how do you write an equation for enthalpy of formation of methane? Write methane 1 mole. It is gas. From its elements, which are the elements of methane? Carbon plus hydrogen. Need to balance. Write 2. This is solid. Gas. Then whatever enthalpy change is there. Generally, it is called enthalpy of reaction. Since this reaction represents formation of 1 mole of substance from its elements, it can be called as enthalpy of formation. It is combustion this is around 75 kilojoules, as I remember. No need to if you don't remember values, you can just write either minus Q kilojoule or plus Q kilojoules. No problem. No need to remember values like that. Okay. Right. So these are all the reactions which represent enthalpy of formation. Okay. So what is that you need to remember essentially in this particular definition? Enthalpy of formation of a substance means 1 mole of that substance should be formed from its elements only. Then it can be called as like for example, if I write this reaction, then there is formation of water. Okay, so around 890 kilojoules of heat is liberated. Can I call this reaction producing water or carbon dioxide? This 1 mole of carbon dioxide is formed. Can I call now enthalpy change as enthalpy of formation of carbon dioxide?
No, sir.
Because it is not being formed from its elements. A particular substance may be produced in different ways, but in order to calculate enthalpy of formation, it should be formed from its elements only. That's the condition. So it's not delta FH. Okay, so that's not. Let's take up next. Similarly, the enthalpy of formation delta FH at 1 bar pressure under given condition of temperature. Generally 298 is taken. It's not specific cause. So enthalpy formation at 1 bar pressure under given temperature is called what? Standard enthalpy of formation. Delta FH. Standard enthalpy of formation. Okay. You need to know certain things about enthalpy of formation. What is that? The enthalpy of formation values indicate stability. Indicate stability of a compound formed. Can anybody tell me how is that? Enthalpy of formation values indicate stability of a compound formed. Okay. During the formation of a particular compound, if heat liberated is more, then that compound is more stable. If heat liberated is less, then that compound is less stable. That's all. Okay. So I can say more the negative value of delta FH. Negative value means exothermic. More the negative value of delta FH, higher is the stability of the compound. Higher is the stability of compound or substance formed. Ah, shit. One second, it's got crashed. One second, it is launching. Excuse me. Ah. More the negative value of delta. You can see the screen, all of you.
Yes.
Ah. More the
Yes, sir.
negative value of delta FH, higher is the stability of the compound formed. Okay. Example. Enthalpy of formation of carbon monoxide is minus 110. Enthalpy of formation of carbon monoxide is minus 110.5 kilojoules. Enthalpy of formation of carbon dioxide is minus 383.5 kilojoules. I have to change the equation. It all depends on how strong is the internet network. Sometimes in the peak hours, 100 Mbps they promise. It will reduce to 15 Mbps, 10 Mbps now. I just thought of completing this line. I don't know the name. I'll just finish up this sentence. Delta FH naught of carbon monoxide is minus 110.5. and that of carbon dioxide minus. So which is liberating more heat? Carbon dioxide. So what is the conclusion? CO2 is more stable than carbon dioxide. That's the meaning. Also, one more thing you just need to know. So enthalpy of formation, standard enthalpy of formation of an element is equal to the enthalpy of the standard enthalpy of the compound itself, or for any substance. Standard enthalpy of formation of a compound is equal to enthalpy of the compound itself. Okay, and you should know one more fact of it, that is standard enthalpy of formation of an element in its standard physical state should always be taken as 0 for all. Let me finish up. Enthalpy formation of an element is taken as 0. Okay, so delta FH naught of like carbon or hydrogen or iron, etc., becomes 0. I'll change the page. So enthalpy of formation values indicate stability. More the heat liberated during the formation of a compound, more is the stability of the compound. And also you should know enthalpy of formation of a compound is equal to its enthalpy. And standard enthalpy of formation of a compound, standard enthalpy of formation of a compound, standard enthalpy of formation of an element is taken as 0 always for carbon, hydrogen, oxygen, nitrogen, any element for that matter, it should be taken as 0 for all calculations. Okay, so that is about enthalpy of formation. Next definition, enthalpy of combustion. Now combustion word is applicable for reactants or products?
Reactants.
Obviously, formation in a reaction is applicable for products. Combustion is for reactants because reactants are burnt. So what is the definition? So enthalpy change that occurs when 1 mole of a substance is burnt completely. Otherwise, enthalpy change will be incompletely liberated, right? So burnt completely. How complete combustion can happen? In excess air or oxygen. Okay, 1 mole of a substance when burnt completely, then whatever the enthalpy change exists, that will be called as enthalpy of combustion of that particular compound. For example, if you want to write an equation for enthalpy of combustion of carbon, giving rise to CO, right? How many moles of carbon we have taken? 1 mole. So this is solid, gas, and gas. So this equation represents combustion of 1 mole of carbon. So therefore, this value, whatever the enthalpy of reaction is there, that can be called as enthalpy of combustion of carbon. So it is minus 383.5 kilojoules. Okay. Now, you people have to tell me, can this reaction, enthalpy change, enthalpy of combustion of carbon, I have told, no? Can this value minus 383.5 kilojoules can be called by some other enthalpy change also?
Enthalpy of formation of carbon dioxide.
Very good. Because this equation also is according to the definition of enthalpy of formation. So 1 mole of carbon dioxide is formed from its elements. So this value can be even enthalpy of formation of carbon. Carbon
dioxide.
So look at that. There are 3 terminologies for minus 383.5 kilojoules. It can be, general term is enthalpy of reaction, particularly enthalpy of combustion of carbon. Also enthalpy of formation of carbon dioxide. Now, I'll write an equation. You should tell me what are all the terminologies that we can give for that particular reaction. Now, this enthalpy change during this reaction can be called by what terms? Can it be called as enthalpy of combustion of methane?
Yes.
Okay. Can it be called as enthalpy of reaction?
Yes.
Can it be called as enthalpy of formation of carbon dioxide?
No.
No.
So this is enthalpy of reaction, also enthalpy of combustion of methane. Sorry, 890.1 kilojoules, but not enthalpy of formation also. So you should be careful. Okay. This is about enthalpy of combustion. So if you have been asked to write an equation for enthalpy of combustion of a particular substance, take 1 mole of that substance, burn it completely to give the terms. Okay. Shall I? Okay. Delta H is minus 110.5 kilojoules. Now, is it enthalpy of combustion of carbon? It is as per the definition.
Yes, sir. It is.
Then what is the difference between first equation?
Formation of enthalpy of formation of carbon dioxide and carbon.
What do you
First
mean?
reaction is excess air.
For me?
First reaction takes place in excess air.
Huh.
So 1 mole of O2. So
Huh.
here the oxygen content is reduced.
So, what is the conclusion?
Product is
My question is, shall I consider this value minus 110.5 as enthalpy of combustion of carbon or not?
No, sir.
No, sir. No.
Why?
Incomplete.
Restricted amount.
What is the definition?
incomplete combustion.
Definition is burnt completely in excess air or oxygen. So this cannot be equal to enthalpy of combustion of carbon. So people have to know. Then what can be it actually? Minus 110.5 can be called by what name? What term?
Formation of carbon monoxide.
Formation.
Your
So
formation of
that is
carbon
equal
monoxide.
to enthalpy of formation of carbon. I don't know, I'm getting off. So I think things are more clear now. Enthalpy of combustion of a particular substance, do you think is it always negative or it can be positive also? What do you mean by enthalpy of combustion of a substance is negative?
Sir, it is stable.
Heat is
Delta H negative means at first sight, what is that? Exothermic, right? So
Exothermic.
delta CH of a substance is always negative. Heat is always liberated. Burning of a particular substance can never be heat absorbing process. Right now. So this is about enthalpy of combustion. Shall we proceed now? Third. Enthalpy of transition. Enthalpy of transition. What is the definition? Transition happens when a substance changes from one allotropic form to another allotropic form. So, 1 mole of a substance when changes from one allotropic form to another, say at the transition temperature, is the condition. So that is called enthalpy of transition. Now, substances, I'm sorry, substances exist in different allotropic forms. You know. Okay. So, for example, carbon in diamond when converts to carbon in graphite, enthalpy of transition delta traj is minus 1.9 kilojoules. Okay, so this represents 1 mole of carbon in diamond getting converted to 1 mole of carbon in graphite. So this is enthalpy change minus 1.9 kilojoules. Okay, now this question, this equation also can have a question like this. They'll give a equations CD giving it to CG delta transition H is equal to minus 1.9. They'll ask you between diamond and graphite allotropic form, which is more stable?
Graphite.
Why?
Energy is liberated.
So if energy is liberated, so stability increases. See, look at that. Diamond is so hard and stable. Graphite is even more stable when compared to diamond. That's the meaning of that. So this is the enthalpy of transition. So like that, you can go for red phosphorus. Okay, this is I remember plus 18. Tell me, which is more stable?
Red phosphorus.
Red phosphorus, because it is endothermic. Enthalpy content of red phosphorus is low when compared to white. So that's why, you know, white phosphorus when exposed to atmospheric condition, what would happen? What happens when white phosphorus is exposed to air? Catches fire. It catches fire. And that's why white phosphorus should never be exposed to the air. And when, you know, you bury dead people, okay, there are different customs. Some people will burn and some people will bury in the graveyard. So when you bury the body, after a couple of years, due to soil erosion and all, due to rain and atmospheric conditions, slowly the bones will come out. Bones contain phosphorus, and that bones, when you know, exposed to atmosphere, the phosphorus content present in it catches fire. Okay, and suddenly, if it catches fire, if a person is walking nearby the graveyard during the night time and see fire, immediate substances catching fire, immediately thinks that something supernatural. Actually, it is just white phosphorus which catches fire. So anyhow, we'll proceed further. This is enthalpy of transition. What is to be remembered? For 1 mole of substance from one allotropic form to another. Combustion, 1 mole of reactant or substance when burnt in excess of air or oxygen. Similarly, formation, 1 mole of substance formed when it is formed from its elements. Okay. In their standard physical state, it becomes standard enthalpy of formation. Like that. Here also, at 1 bar pressure and given temperature, the enthalpy, respective enthalpy can be standard enthalpy change, standard enthalpy of transition, standard enthalpy of combustion. Okay, we'll take next. Fourth. Okay, enthalpy of dissociation. Or ionization. Enthalpy of dissociation or ionization. Delta DH, or they say DSH. Okay. What is this? See, enthalpy of dissociation means when 1 mole of any substance dissociates into the solution, into respective ions. Okay, that's all the enthalpy of solution. For example, NaCl when formed, when added to aqueous medium, it becomes Na plus aqueous plus Cl minus aqueous. Then whatever the enthalpy change is there, enthalpy change is plus 5.45 kilojoules. So much heat is absorbed, enthalpy of dissociation. So when 1 mole of solute dissociates into its ions in aqueous medium is what is enthalpy of dissociation. Now this also can be called as enthalpy of solution. Enthalpy of solution. There is one more definition, that is enthalpy of solution at infinite dilution. Enthalpy of solution at infinite dilution, you should call that. Okay, what is enthalpy of solution at infinite dilution? Now same definition. So whenever 1 mole of a solute is dissolved in a solvent, it ionizes. But one extra condition, where enthalpy change that occurs when 1 mole of a particular substance is dissolved in a suitable solvent, such that further addition of solvent will not produce any more heat change. Further addition of solvent will not produce any more heat change. Then the enthalpy change is called enthalpy of solution at infinite dilution. Okay, so same equation, for example, you can write NaCl plus aqueous, it gives Na plus OH minus Cl minus okay, but what is the condition? If you add solvent at any stage of dilution, add excess solvent, heat change should not be produced. Then that point is called enthalpy of dilution at enthalpy of solution at infinite dilution. Okay, so 1 mole of solute when dissolved in a solvent such that addition of solvent will not produce any more heat change. That's called enthalpy of solution. Okay, so just know about it. We'll take it further. This enthalpy of solution can be calculated also as lattice enthalpy plus enthalpy of hydration, like that. Just know this. What is lattice enthalpy? Hydration enthalpy we'll just have in a while. Okay, fine. We'll take up further. This is enthalpy of dissociation, and similar to that is enthalpy of solution at infinite dilution. Next we'll take up fifth, third, fourth, fifth. After this we have enthalpy of neutralization. What is enthalpy of neutralization? Neutralization means what basically? Reaction between acid and a base. Now, whenever acid is neutralized by a base, in that reaction, there will be enthalpy change. The enthalpy change that occurs during the neutralization, enthalpy of neutralization, but you have to have a condition. In all the previous definition, we have taken 1 mole of the substance, whether it is formation, combustion, transition, solution, 1 mole. Here, we have to take 1 gram equivalent mass of an acid when neutralized by 1 gram equivalent mass of a base. Okay, then it is called as enthalpy of neutralization delta NH. Okay, so for example, when you take HCl, add to the sodium hydroxide, it becomes NaCl and water. You should not take 1 mole. Instead, you should take 1 equivalent mass. 1 equivalent mass. When 1 equivalent mass of an acid is completely neutralized by 1 equivalent mass of a base, then the enthalpy change here is called enthalpy of neutralization. And of course, it is found to be how much? Anybody remembers? How much is enthalpy of neutralization of HCl by NaOH? No idea. 1 gram equivalent mass of an acid is completely neutralized by 1 gram equivalent mass of a base, where in solid state they can't react, right?
57 kilojoules or something.
Correct. So 1 gram equivalent mass of a base, where that reaction has to happen in dilute aqueous medium. Base in dilute aqueous medium is the definition of enthalpy of neutralization. I'll repeat. Enthalpy of neutralization is the change in enthalpy that occurs when 1 gram equivalent mass of an acid is completely neutralized by 1 gram equivalent mass of a base in dilute aqueous medium. So take 1 equivalent mass of HCl and NaOH and mix them. Heat liberated is 57.3 kilojoules. What I'll do, I'll take next HNO3. I'll mix it with OH. Certainly both are different acids and bases. When I mix these two, what is the salt expected? Potassium nitrate and water. Okay, so enthalpy of neutralization is equal to, in this particular case also, heat liberated is 57.3 kilojoules. Alright, what is this? Okay, let me change the combination and see if it is same. Okay, I will take HCl and KOH, KCl and water. Here also heat liberated is 57. How come? There is one concept attached to this particular thing. Tell me, what is it? What is that you can remember from this? Enthalpy change or enthalpy of neutralization remains a constant. In which case? HCl is strong acid or weak acid?
Strong acid.
OH?
Strong base.
Why do we call these substances strong?
Once if they dissociate, they will again recombine to give the same product, sir.
No, strong electrolytes concept, that's all. Strong electrolytes means substance which dissociate completely. After evaporation, they may give back. That's the thing. So strong electrolytes are substances which dissociate completely. Weak electrolytes dissociate partially. So strong acid, strong bases means substances which dissociate completely. Sorry. So these are all strong acids and strong bases, whatever we have taken. So it simply concludes that whenever a strong acid is neutralized by a strong base, heat liberated is always a constant. 57.3 kilojoules of heat is liberated. If it is a weak acid and weak base, then the heat liberated will be less. For example, CH3COOH plus sodium hydroxide giving rise to CH3COONA plus water. So enthalpy of neutralization is somewhere like 55.4 kilojoules. Heat. So look at that. So 57.3 was expected, but it is 55.4. So obviously it means that heat liberated less means one of the acid or base or both could be weak. So here it's a weak acid. This is strong base. So it simply means that whenever neutralization reaction takes place between the weak acid and the weak base, heat liberated would be less than 57.3 in magnitude. Okay, so what is the reason? Anybody? excuse me. Any idea? Why, first of all, why enthalpy of neutralization is constant in case of strong acid and strong base, and why it is different or less in case of weak acid and weak base? No idea.
Weak acid does not dissociate completely.
So what?
Sir, can you repeat the question, sir?
Question getting repeated now. Why enthalpy of neutralization of a strong acid by a strong base is constant, and why it is not constant in case of weak acid and weak base? Okay, we'll answer first part. Why it is constant in strong acid and strong base?
Sir, in strong acid, strong base, only forward reaction occurs. There is no backward reaction possibility only.
In case of weak acid and weak base also only forward reaction taken, because salts by and large are strong. They doesn't again dissociate to give acid and base.
Sir, the reactants completely react.
You think here it is incompletely reacted? Acetic acid, sodium hydroxide to give sodium acetate and water. It's complete reaction only have written. So
No reactant will remain unreacted, sir.
here also reaction is completed.
Okay.
Yes. Excuse me, people of VVS2, ladies and gentlemen.
It is the maximum extent it can reach.
Well, you were telling something. It is the maximum extent.
Like it, no, I don't know how to say.
That's a good answer. I say you can get complete marks for that.
Sir, complete ionization for strong acid and strong base, sir.
So what?
Sir, like a strong acid and strong base.
So
Strong
women friend of India. Women friend of India.
Sir, whatever the acid or the base, the amount of ions, there is complete ionization. So formation enthalpy is constant, sir.
Once again, repeat it.
Sir, for any strong acid or strong base, the extent of ionization is the same, sir.
Okay.
It ionizes completely.
So
Enthalpy of formation is constant. The same number of ions are getting converted to salt and water.
it is quite general. It's not specific. So out of 3 marks, you will get 1 mark.
Enough.
Idiot. Is it enough, man? So 1/3 is enough, man. 35 marks is enough, man. Thank you. Sandra?
So is it to do with the 1 gram equivalent mass? That we're taking strong acid and strong base is 1 gram equivalent.
It is by definition for weak acid, strong base, anything is 1 gram equivalent mass only.
Sir, for the weak acid to ionize completely, extra amount of energy is used, sir. So the enthalpy, negative enthalpy decreases.
Why it is constant in strong acid and strong base?
No extra energy is used for ionization.
There is no hydrolysis in case of strong acid, strong base.
Okay. Madam Neeti Gandhi?
Yes, sir.
Oh, you are present, huh?
Yes, sir.
No, I'm asking the question. Priyanka Gandhi?
Sir, one doubt, sir. Is it constant for weak acid and weak base also? It
No.
varies.
Yeah. Now you can answer. Nikita?
Yes, sir. It has to do with the other energies required to complete the reactions.
But
So, it is like constant because no energy is required for it to complete the reaction.
Okay.
So it is constant for
Okay. So since we were discussing long on this enthalpy of neutralization, somebody left the meeting. It's 49 became 48. If I continue, only one will be remaining. That's me. Okay, let me explain. Okay. See, okay. Some of you have closely explained, not exactly. Now we need to answer two questions here. Answer two questions. What is that? Why enthalpy of neutralization of a strong acid by a strong base is constant? If you can answer this correctly, then other part of it can be easily answered. No problem. Why it is constant? How much is that? Enthalpy change is minus 57 kilojoules. Heat liberated, you have to represent minus, because liberated, when we are mentioning in a sentence, you should write only magnitude. Heat liberated during neutralization of strong acid, strong base is 57 point. Enthalpy change for enthalpy of neutralization is minus 57 point. Why it is so? It is simply consider the case. Consider neutralization of HCl, a strong acid, and NaOH, a strong base. Okay. Now, for enthalpy of neutralization, we'll take one equivalent mass of HCl, right? One equivalent. Is equivalent mass of HCl same as 1 mole or 1 molecular mass? One equivalent mass of HCl same as 1 molecular mass or different?
Same.
Same, sir.
Why?
So the number of replaceable hydrogen is 1.
Exactly. Exactly. So equivalent mass is equal to molecular mass divided by basicity of the acid. There is basicity 1 as it has only one replaceable hydrogen. So equivalent mass is equal to molecular. So when one equivalent mass of HCl is taken, how many moles of H plus ions will be obtained? 1. So in a solution, I have taken a beaker, water, dissolved one equivalent mass of HCl. It dissociates completely, it's a strong acid. It produces 1 mole of H plus ions. So in a solution of one equivalent mass of HCl, there is 1 mole of H plus ions. Correct? This is the beaker. Okay. Next, NaOH. One equivalent mass of NaOH. Is NaOH also, in case of NaOH also, molecular mass, equivalent mass are same? Boys and girls?
yes, sir.
Yes.
Because acidity is 1.
1.
Equivalent mass of the base is equal to molecular mass divided by acidity, 1. So both are same. So one equivalent mass of NaOH I have taken, see, beaker. Okay. So this has one equivalent mass of HCl. This has one equivalent mass of NaOH. So in this solution of HCl, there is 1 mole of H plus ion. In this solution of NaOH, there is 1 mole of OH minus. So for neutralization to take place, what do? We are going to mix this. Correct? When we mix, it gets neutralized. The volume gets doubled. So now, actually what happens during neutralization? I will not incorporate HCl and NaOH molecules because it is no more molecule now in the solution. They are present as ions. So neutralization. After mixing, neutralization takes place. What is neutralization? H plus Cl minus plus Na plus OH minus. They combine to give what, man? NaCl and water. But this NaCl is again salt. In the aqueous medium, it remains as Na plus and Cl minus. Now, the ions which are there before the reaction and after the reaction are called spectator ions. They simply are there to see. Okay, they get cancelled. So therefore, during neutralization of a strong acid and strong base, the net reaction that takes place is only the combination of H plus ions from the acid, 1 mole, and OH minus ions of base 1 mole to form 1 mole of water. Okay, so 1 mole of H plus ions of the acid combines with 1 mole of OH minus of the base to form 1 mole of water. Whenever 1 mole of water is formed from its ions, not from elements, from ions, enthalpy change is always a constant, 57.3 miles. Now let us look back. Look at this. HCl combines with NaOH, 1 mole of water. HNO3 combines with KOH, 1 mole of water is formed from its ions. That's why it is 57.3 kilojoules. So the net reaction that takes place during any neutralization reaction of a strong acid and strong base is combination of 1 mole of H plus ions with 1 mole of OH minus ions to form 1 mole of water, during which heat liberated is always a constant, that is 57. Okay, so this explains a constancy in the enthalpy of neutralization of strong acid base, strong base. So since 1 mole of water is formed always during, sorry, excuse me for my handwriting, formed always during neutralization of strong acid by strong base, heat liberated, enthalpy of neutralization is constant, that is minus 57.3. Okay, 57.3. Is it okay? So this is about why heat liberated. Now people have to tell me. I'll just take an example pertaining to this. For the salt, how many moles of water? So what is enthalpy of neutralization? How much, man? See, 1 mole of sulfuric acid has 2 equivalent masses. There are 2 replaceable hydrogen atoms. So combines with 2 moles of KOH to form K2SO4 and 2H2. So it should be minus 2 into 57.3 kilojoules. So why in case of sulfuric acid, double the amount of heat is liberated? For the reason that 2 moles of water. Is that okay? Now, first part is answered. I think you have understood. Any doubts there? What? All of you are went?
No, sir.
Then,
No, sir.
No doubt.
So now, what is the next question for us? Why
Why it is not constant for V?
enthalpy of neutralization? I would better say heat liberated, because enthalpy of neutralization is negative. Why heat liberated during, that is during neutralization of weak acid by a weak base is less than 57.3 kilojoules. I think now you can explain. Some of you also have explained almost correctly why it should be like that. Now I'll take the same example. Acetic acid, NaOH. The reaction expected is sodium acetate and water. Now weak is acetic acid. This is strong. I have taken 1 equivalent mass of both. Now this completely ionizes, complete dissociation, to give 1 mole of OH minus. Okay, 1 mole. How about this partial? Partial dissociation, because it's weak. Weak electrolyte dissociate partial to give H plus ions less than 1. One second. It gives less than 1 mole. I think the page is overloaded now. Just see how much. Oh, I think it is overloaded. This much it can't take. Okay. Anyhow, I'll try to complete this. So, acetic acid is a weak electrolyte, dissociate partially to produce less than 1 mole of H plus. Now, this H plus and OH minus combine to form water, which is less than 1 mole. When 1 mole of water is formed from its ions, heat liberated is 57.3 kilojoules, enthalpy of neutralization. And now it will be less than 57.3 kilojoules right now. So heat liberated, since if I write enthalpy of neutralization, negative sign comes. When I say less than negative minus 57.3, it becomes different meaning. So because it is negative, so I just write heat liberated is less than 57.3. Now what would happen? Why it is less than 57.3? You can also explain like this. Expected amount of heat liberation is 57.3. A part of heat would be reabsorbed by undissociated acetic acid molecules to undergo complete dissociation. Now, how much ever is reabsorbed by acetic acid molecules to undergo complete dissociation, that much wouldn't be evolved. That's all. Approximately here 1.9, actually 2 kilojoules of heat is reabsorbed by acetic acid molecules, undissociated. That's why that much amount of heat is less liberated. Okay. So what I can conclude is a part of 57.3 kilojoules of heat is reabsorbed by weak acid, or if it is weak base. Okay. So that heat liberated is less than 57.3 kilojoules. If both acid and base are weak, then heat liberated will be much less, because both of them would reabsorb. Okay. I think someone has given this answer for weak acid and weak base. That's the correct one. Okay. So this is the reason. Two things: why strong acid and strong base neutralize to give always 57.3. That's because during neutralization of strong acid by strong base, when I say that, it is always one equivalent mass of both. 1 mole of water is formed from its ions, where heat liberated remains constant. During weak acid and weak base, which dissociate partially, a part of heat of 57.3 would be reutilized for complete ionization of a weak acid or weak base. How much ever reabsorbed, that much wouldn't be liberated. So that explains why enthalpy of neutralization is less in case of weak acid and weak base. So therefore, for a weak acid or a weak base, enthalpy of neutralization can be calculated using this formula: 57.3 kilojoules plus enthalpy of ionization. How much ever heat is absorbed for ionization, that much wouldn't be liberated. INH is enthalpy. Just now, enthalpy of neutralization of a weak acid or weak base, 57.3 is expected liberation, but some part of energy is reabsorbed, ionization. So that much will be not liberated. In case of acetic acid, around 1.9 kilojoules of heat is absorbed for ionization. So what would be that? 57.3 plus 1.9 would be 55.4. Okay. So this is about enthalpy of neutralization of a strong acid, strong base, weak acid, weak base, and all these things. Okay. If you have any doubt, you can ask me. Otherwise, I'll proceed to next page. Any doubt?
No, sir.
No. Okay. I'll switch off my video. Let's see what internet is very. I'll proceed with further definitions in thermochemistry. Okay. Next is enthalpy of of atomization. Delta AH. Okay, enthalpy of atomization. Here there is a change in enthalpy when 1 mole of a gaseous compound, when 1 mole of a gaseous compound is converted to gaseous atoms. It is a change in enthalpy that occurs when 1 mole of gaseous compound is converted to gaseous atoms. For example, when we take this methane, okay, so you take 1 mole of methane, of course it is gas. If it is the substance taken is solid, you have to convert that one into gas and then break that one into gaseous atoms. Carbon gas and 4 hydrogen gas. When you convert this methane gas to carbon and hydrogen gas, then whatever the enthalpy change is there, that is called enthalpy of atomization. Here it is 1.1665 kilojoules. So this is the amount of heat absorbed for that. So that is enthalpy of atomization. There is one similar definition, that is bond enthalpy. Bond enthalpy, delta BH. What is bond enthalpy? Again, you have to break 1 mole of bond. So enthalpy change that occurs when 1 mole of bonds are broken to form the products, gaseous. Then it is called enthalpy of bond enthalpy level. For example, when you take this methane case itself, okay, you have to break 1 mole of bond of particular type. You just break 1 mole of CH bond. What is remaining now? CH3 gas and H gas. You have broken now 1 mole of CH bonds, correct? You have broken this. Then whatever the enthalpy changes there called, it's called bond enthalpy. It is some 2 kilojoules, some 400 or something like that it comes, 435 or so. So that is the bond enthalpy. Okay. So now I'm going to break 1 more bond from CH3. Okay, CH3 gas. I'm going to break 1 more bond, CH2 gas plus H. Now people have to tell me this bond enthalpy. Okay, I'll call it as Q1 and this is Q2. Are they same or different? Q1 is equal to Q2 or not equal to Q2?
They're not the same.
They will not be same. Okay, so Q1 would not be equal to Q2. Okay, so like that, if you keep breaking further bonds, so the enthalpy changes will be different. In such cases, you know this atomization enthalpy, right? This atomization enthalpy of methane indicates enthalpy change that is required to break all the 4 bonds. All the 4 bonds. Here only 1 bond is. So every bond you break, heat required is different. In such cases, average bond enthalpy will be calculated. Okay, so therefore, average bond enthalpy is equal to atomization enthalpy, that is for 4 bonds divided by 4u. Is that okay? So that is 1665 divided by 4, how much ever it is there. So around 466, somewhere like that it comes. Okay. So this is how we calculate average bond enthalpy by knowing atomization enthalpy. Okay. One more thing you should know. By knowing bond enthalpies of reactants and products, you can calculate enthalpy of reaction also. Okay. So also enthalpy of a reaction can be calculated using bond enthalpy values. So bond enthalpy values of reactants. This is used in problem solving, and bond enthalpy values of products. Okay, like this. For example, when you take you know something like C2H6 plus say O2 giving rise to 2CO2 plus 3H2O, it is 7 by 2, right? This is the reaction for which if you want to calculate enthalpy of reaction when bond enthalpies are given, so it can be written as enthalpy of reaction is bond enthalpy of reactants. Now, which are the reactants here? Ethane and oxygen. Okay. When I say ethane, the structure is, sorry, the structure of ethane is C bond C, and totally how many CH bonds are there? 3 plus 3, 6. Right. Okay. So I would write bond enthalpy of reactants. Which are the reactants here? I can also write bond enthalpy as BE of C2H6 for just representation sake. Becomes easy. 7 by 2 times bond enthalpy of O double bond O. These are the reactants, right? So minus, which are the products? 2 times bond enthalpy of carbon dioxide plus 3 times bond enthalpy of OH bond. But each molecule of water has how many OH bonds? 2 OH bonds. So it is better to say 2 into 3. Okay, because it is like this. I will let you know. This OH has, water has 2 OH bonds, right? How many water molecules have been formed? 3. 3 into 2 into bond enthalpy of OH bond, you have to take like this. And that too, in case of bond enthalpy of ethane, how many carbon-carbon bonds are there? 1. That also you should take bond enthalpy of Cc plus how many CH bonds are there? Totally 6. 6 into bond enthalpy of CH. Likewise, 7 by 2 times bond enthalpy of O bond double bond O, and then this thing. Okay, same thing. 2 times bond enthalpy of carbon dioxide. Here also, sorry, carbon dioxide also C double bond O, right? How many are there? 2 into this. Let me write that part here like this. What it becomes? 2 times into 2. 2 times into 2 because 2 carbon dioxide. Bond enthalpy of C double bond. Plus 3 into 2 times bond enthalpy of OH. This much is the thing. They would have given bond enthalpies of CC bond, CH bonds, O double bond O, C double bond bond, OH bond. Substitute and simplify. Get enthalpy of reaction. Is it okay? So that's about bond enthalpy concept. Okay. See, after this, there are different definitions. You can analyze by common sense. For example, enthalpies of phase transition, we say. Enthalpy of phase transition. Phase transition means what? When a substance changes from one phase to one physical state to another. What do you mean by, for example, enthalpy of vaporization? What do you mean by that? It is a change in enthalpy when 1 mole of a liquid converts to gaseous state at its boiling point. Correct? No? That is vaporization, because vaporization is liquid to gas. Similarly, enthalpy of fusion means what? What could be enthalpy of fusion? Change in enthalpy when 1 mole of a solid melts into liquid at its melting point. Correct? No? Enthalpy of sublimation. What could be enthalpy of sublimation? Change in enthalpy that occurs when 1 mole of a solid converts to gaseous state without entering into the liquid state. Enthalpy of sublimation. So something like that. Similarly, enthalpy of hydration comes. Enthalpy of hydration is not under phase transition. What could be enthalpy of hydration? When 1 mole of a substance is dissolved in water. So when all the ions are completely hydrated, means surrounded by water, then whatever the enthalpy change is there, that is called enthalpy of hydration. So fine, with these many definitions we have taken in different enthalpies of reactions. So in our next class, we are going to take up Hess's law and Lavoisier-Laplace law. Oh, still it is 3 minutes. People are leaving. At what time you will have class in the college?
9:30.
9:30. Okay.
Yes,
No
sir.
problem. I have 2 minutes more. No problem. In the next class, Hess's law and Lavoisier-Laplace law and related problems we'll take up, and then we'll go to next part of thermodynamics. Okay. So bye. We'll meet for the next class. Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you.